Guys, in this particular screencast, what I wanted to go over was how to find if a function has something called even symmetry. So what we're actually going to take a look at here is the idea of what the definition is of even symmetry from an algebraic perspective, and then we're going to actually look at how to use that definition here to come up with whether or not a function really does have even symmetry without graphing it. So the first step that we're going to do is we're going to look at the definition. Well, a definition says that if you have a function f of x, the function itself is actually symmetrical if you get the exact same thing as this right here, which is basically saying if you take the inverse of your input and make it a negative, you should get the exact same thing as your output. Okay, well, if you think about what that would look like in terms of an xy table, remember, all of this is saying for a function that's already even, you're basically saying that if you give an input of 1 and get an output of 2, then giving an input of -1 should also give you an output of 2 as well. Well, what exactly does that look like when you try to use this in practice? So what we're going to do is take a look at this example here. Determine if the function f of x equals x squared plus 3 has even symmetry. Well, if it has even symmetry, we should be able to use the definition to our advantage. Well, we can see right here we already know what f of x is. So looking at the first part of the definition, we already have f of x. What we need to know is, does f of x equal f of negative x? Well, we don't know what f of negative x is, so we need to go and actually take a look and see what that looks like. So what I'm going to do is I'm going to take negative x and plug it in to the rule right here. So since I'm plugging it in or evaluating the function, remember I'm going to have to use parentheses when I do a substitution. So I'm going to put x squared plus 3 right here, and then I'm inputting it in as negative x. Well, thinking about what that would give me, this would say, okay, take this x that's inside of the square along with its negative sign and square it. So negative x times negative x is going to give me a positive x squared. And then the plus 3 just comes right down. Well, if you take a look at f of x up here, you see that f of x is equal to x squared plus 3. And you also see that f of negative x is equal to the exact same thing. So what that tells me is that f of x is equal to f of negative x. Does that match what our definition says? It matches our definition exactly, so our answer here is yes. The function f of x has even symmetry. So I'll write down symmetry right there. So that shows us an example of what it looks like when it does have even symmetry. Now let's go and take a look and see what happens when we have an example of something that we're not quite so sure about. So when we look at this function here, we're going to start with the same idea. We already see that we have f of x right here. We know it equals this right here. From our previous example, we already saw that what we can do is just simply substitute in negative x and take a look and see what happens. So we get negative 4, and we're substituting in something for x squared, plus 3, substituting in something for x, and then we also get plus 5 right here. Putting in what we substitute for, we get negative x right here, and we get negative x right here. So looking at what we get on the right-hand side when we just do our order of operations, I get negative 4, and this exponent here is going to cause this to be simply x squared, which is positive, plus 3 times negative x is going to be plus negative 3x plus 5. Cleaning up all of our multiplication here and any unnecessary things like this plus negative right here, we're actually going to get negative 4x squared minus 3x plus 5 for this f of negative x right here. Now, looking at what this means, I see negative 4x squared as the very first term right here, and that's exactly what I see inside of f of x. But when I look at my second term, I get this negative 3x. Well, up here, it was actually a positive 3x. And then I get a plus 5 and a plus 5. Well, unfortunately, this negative 3x right here and the positive 3x right here do not match up. So what this tells me is that f of x does not equal f of negative x, which means it can't fulfill the definition of having even symmetry. Because it doesn't meet the definition, it means it's not even symmetry. So we would actually say that no, this does not have even symmetry. So overall, when you're looking at checking to see if something has even symmetry or not even symmetry, all you're going to do is simply take the original function, plug in negative x, then do any algebra to simplify it down until you have everything back to just a bunch of negatives if you need them, plus if you need it, and then once you get it, compare f of x back up to f of negative x, and if they meet this definition right here, that means that it has even symmetry.